We operate under a perfectly rational assumption, don't we? That adding new, helpful features to the platforms we rely on naturally makes them better. But what if it doesn't? What if these very upgrades are the exact things triggering catastrophic failure? It isn't a symptom of bad code, it's not careless developers. It's something hidden, something much deeper in the architecture itself. Think about it. When a team of software engineers updates an interface, their intent is entirely focused on assisting you, the user. They add an early warning alert, a nested menu, a highly detailed dashboard. Every single addition is completely logical and designed to solve a problem. Yet when we step back and look at how complex systems behave in reality, a disturbing pattern emerges. These helpful, carefully designed additions are frequently the direct catalyst for total collapse. The upgrades don't just fail to help, they actually induce the failure of the system itself. Take the infamous 3 Mile Island nuclear accident, for example. Investigations later concluded that it wasn't strictly a mechanical failure that doomed the plant. The design of the human-machine interface itself essentially paved the way for the meltdown. The operators were completely overwhelmed by a system that was, theoretically, providing them with absolutely everything they needed to know.
And we see this exact same strange contradiction playing out in the sky. In modern aviation, manufacturers are constantly upgrading to new, non-standard flight instruments or adjusting throttle layouts. Again, the goal is better human-machine interaction. But these supposedly superior designs have repeatedly caused highly trained veteran pilots to make fatal errors. A conceptually brilliant idea yields a devastating result.
So why does added functionality actually cause failure? Well, to figure that out, we have to temporarily ignore the users. We need to forget the specific, tragic context of these accidents and look exclusively at the silent, structural flow of information. Section 1. The physical bottleneck, a constraint on flow. Let's look at a completely different, purely physical system. Imagine a basic physical pipeline, one that routes a constant flow of liquid into a container. At the very end of this pipeline sits a funnel. The neck of this funnel is entirely rigid. Based on its physical diameter, it can only pass a highly specific, fixed quantity of material at any given moment. Let's say exactly 7 units of liquid. Now, because this physical bottleneck is fixed, it literally doesn't matter how much pressure builds up behind it. You could hook up a dozen extra pipelines to the top, but the physical exit rate at the bottom simply cannot be expanded. If you force 10 units of liquid into a rigid space built for 7, it doesn't miraculously speed up, it spills over. The entire flow breaks down. Section 2. Rational accumulation, local optimization. Let's step away from the physical pipeline for a moment and observe how our modern digital environments are actually built. Developers naturally follow a highly effective, logical loop. They design a user interface, test it with real people, analyze the quantitative results, and repeat the cycle. It makes perfect sense, right? It's the absolute foundation of human-computer interaction. Through this relentless iteration, the number of features inevitably increases. Every time you test a system, you're going to spot a friction point. And the logical, rational solution to friction is to add a small feature to smooth it out. Each new addition makes perfect sense on a local, isolated level. But as this cycle repeats itself across months and years, the digital environment naturally grows denser. Menus get nested inside other menus, options expand, dashboards crowd with more and more alerts. What started as a clear path slowly morphs into a dense, overlapping web of very helpful features. And then, suddenly, the system stalls. Multiple digital pipelines are now trying to route into a single, fixed space. The user is bombarded with an escalating volume of completely necessary information, which immediately backs up the flow. Structurally, our digital system is now acting exactly like that physical pipeline on the verge of bursting. Section 3. The biological limit, the invisible funnel. This escalating pressure brings us directly to the hidden constraint that governs all of our digital systems. Way back in the 1950s, research demonstrated an unyielding rule about human biology. It turns out human short-term memory acts exactly like our rigid physical funnel. We are generally able to hold only 7, plus or minus 2, units of information in our active processing center at any given time. 7 units. That is the hard, unchangeable physical diameter of our internal funnel. This reveals the core structural mechanism at play here, cognitive load. Rather than getting bogged down in theory, just think of this as the sheer effort actively being used in your working memory. It dictates the strict biological limit of your processing capacity. You can't just casually decide to process more data, just like a rigid metal pipe can't suddenly decide to stretch.
Think of this effort as being divided into two distinct parts. First, there's the baseline mental work required to actually perform a task, like calculating a complex math problem or flying a commercial jet. But second, there's the extra effort required merely to navigate the interface itself, to read the layout, decipher the menus, and process the warning alerts.
And here is where the structural collision happens. On one side, we have infinite software expansion. Developers can endlessly iterate and add new features to a screen forever. But on the other side, we have finite human processing. As those developers rationally keep adding features, the mental effort required just to navigate the interface expands. And that directly squeezes out the finite space you actually need for the task itself. The funnel fills up with the interface, leaving literally zero room for the actual job.
Section 4. Inevitable lock-in. Reaching the threshold. We've unknowingly engineered a scenario where infinite digital expansion is on a direct collision course with an unyielding biological bottleneck. When that hard capacity of 7 units is breached, the flow just shatters. A heavy cognitive load creates inevitable structural errors. When working memory is overwhelmed, excess information gets violently pushed into subconscious processing. This triggers uncontrollable interference. The pilot doesn't pull the wrong lever because they're suddenly careless. They pull it because the pressure in the funnel has structurally compromised their working memory.
The terrifying part? We can infinitely iterate our software. We can add endless memory and processing speed to the machines themselves, but we can never, ever increase the diameter of the human brain's processing funnel. That biological limit, it's locked in.
Because iterative design almost always operates by adding things rather than taking them away, these interfaces will structurally accumulate features over time. It is a completely irreversible trajectory. The system will just keep accumulating helpful additions until it hits the precise physical threshold of human collapse. So when the interface becomes overwhelming, when the nuclear plant operators freeze in place or the veteran pilots make a fatal error, was the system ever actually failing? Or was it simply following an inevitable trajectory toward an irreversible physical lock-in? The interface was never actually broken. It was just perfectly executing its structure.